Good afternoon, everyone, and welcome. I'm Kathy Wells, Editor-in-Chief of OEM Off-Highway and Equipment Today. I'm excited to be moderating today's session on system-level electrification and the integration of hydraulics, controls, and power electronics. As many of you know, electrification is no longer just about swapping out a diesel engine for an electric motor. Real progress is happening at the system level, where hydraulics, controls, and power systems are designed to work together in a much more integrated way. Today's discussion will focus on what that actually looks like in practice. We'll explore how leading organizations are approaching system-level design, what's changing in the relationship between these technologies, and what lessons are emerging from real-world implementation. We'll also dig into the engineering decisions that have the biggest impact on efficiency, performance, and overall reliability. I'm joined today by two experts who bring deep hands-on experience in this space. Shane Fauché is Business Development Manager for Electrification at Applied Engineered Systems, where he works closely with teams across the country to support electrification strategies. And next up, Joseph Budden is E-Hydraulics Portfolio Manager at Danfoss Editron, where he focuses on integrating hydraulic and electric systems to drive performance and efficiency. Gentlemen, thank you both for being here today. I believe we'll just go right ahead and get started. Jump in with our first question. Why is system-level integration so critical in electrified machines, and where do you see teams maybe falling short today?
Yeah, I guess when it comes to system level integration for electrification machines, the approach needs to be holistic. So it has to be a top to bottom system design. For diesel engines, their size based upon their max expected horsepower. For hybrid electrification solutions, the sizing is based upon maximum efficiency. And it's a dynamic design, so every portion of that system has to be designed as such. In the case of electrification, every watt matters. So we're looking at ways to enhance runtime, thermal management, safety, function control, providing the best power on demand solutions while reducing any potential waste. Where we see things falling short is kind of the current bolt-on mentality. If I need a different part, I just bolt it on. I don't look at potential savings, such as optimized hydraulics for the entire system or the system level approach. Some other shortfalls, or when you piece it together, a motor, inverter, battery, or hydraulics from different sources, there's no integration there. There's no communications thought up front. So getting all that to work together through different system level integrators or providers makes it difficult for everything to come together seamlessly. That's where a system integrator really comes into play. And the last thing really is understanding duty cycles. There's a big mismatch between theoretical duty cycles and actual realistic duty cycles. I walk in at 7 a.m., I turn on the machine, I leave at 5 p.m. My duty cycle is 100%, which is normally not the case. And when it comes to electrified systems or hybrid systems, duty cycles have a huge impact on mitigating the size of that system.
Yeah, well said, Shane. I think that's an excellent series of things that you brought up there. One other thing that I'd want to make sure that I'm also adding to this is that it really does take a team of experts in order to get there. You mentioned this a bit on system integrators, but just to illustrate the point, if you're talking about electrifying a machine, you're talking about somebody who has to be your expert in power electronics, somebody who's your expert in if it's got work function and it's off highway, hydraulics. You need your propel experts, you need your system control experts, and you need somebody that can get all of that at the application level that your customers are working on. So that way they have that deep level knowledge on the application as well. So making sure that you have a team that understands all of those pieces, how they fit together, is really critical in order to be successful. And more we're seeing the demand from OEMs moving to the tier one suppliers to act as that component supplier or that system supplier. The other thing that I think really drives decisions today and places where people can fall down is at the very, very onset of the project. Understanding what your project goals are to start and what your constraints are is essential in order to have a successful project. If your goal is to have a new EV vehicle out on the market in the next 3 months, you're going to necessarily make some trade-offs in order to make that timeline. If your goal is to have an EV platform that you're going to build on over the next 20 years, you might take a different tact to that.
Great
Well
points
put.
here, guys. Let's kind of add another layer to that. So let's talk about how has the relationship between hydraulics controls and power electronics evolved as electrification has advanced?
Yeah, I think this is a natural evolution between the three of them. Um, Back in the day, hydraulics used to just be, mechanical levers that you're moving, but electric controls have been around for quite some time. Moving into smarter control systems and advanced hydraulic systems is a natural evolution of that. And when we start talking about electrification, where, as Shane said previously, every watt matters, um, you need to start thinking about those more advanced systems and those more advanced control architectures to really give the customer and the end users the biggest bang for the buck. Of course, that must be balanced with the return on investment for your customer and the total cost of ownership for the person who's going to run this. If you have a really, really, really advanced system and it makes a lot of sense in theory, if it can't make sense for somebody to buy it, we're just doing science projects. We're not actually advancing the industry.
Yeah, that's definitely well put, Joseph. And like you mentioned before, because of our backgrounds with the companies that we're involved in, fluid power is kind of our backbone. So when we're looking at some of the off-road market applications, we're actually using the baseline of fluid power to convert that to some kind of electrification or hybrid system. So bringing those expertise to the table is unbelievably important and making sure that system integration is kicked off seamlessly.
Okay, moving over to focus a little bit more on hydraulic optimization and those controls. What are the most effective strategies for optimizing hydraulic systems in electrified equipment?
I'll go kind of back to what I mentioned before is the dynamic system solution. So when we look at any kind of system solution, we want to look at everything, especially optimizing the hydraulics. Sometimes electrification is a great idea. Sometimes it's better to go hybrid. Sometimes the solution is just let me optimize my hydraulic system, and that will solve my business need for that particular application. When we talk about that dynamic solution, there's so many different functions that can be involved in it. As we combine electrification into a project, we look at things on an electrification system that we can control through software versus hardware. For a hydraulic system, I may need to add a bigger pump or a different cartridge valve to bring higher flow. For an electrification type driven system, I can do that through software by just increasing RPM. I can also do control ramping, soft shifting, power and demand, torque limiting, and other functions that I can do within a software for an electrification system that on your other hydraulic system will require actual hardware changes. So it allows more optimization in these type of systems that we didn't have before without specific hardware changes.
Yeah, the only thing that I think I would add there is, as I alluded to earlier, there are some places where it's starting to make sense to use some of these really sophisticated architectures like common rail systems, or some really really efficient pumps that are directly actuating controls of different applications. Those can make sense, but again, it's going to come down to the ROI and TCO. That's really what's going to drive it there. The only other thing that I really want to make sure that I'm saying on this topic as well is, um, as Shane alluded to, there might be some applications where today it doesn't feel like they're ready to electrify yet. And that's okay. There's some applications where they're not. Um, but this is a very, very dynamic market, and it's a very, very dynamic area of development. So even if today you're thinking my application will never make sense to electrify, you still have to be very careful about what's out there in this space because it is evolving so quickly. Um, Totally dismissing electrification out of hand, I think you're kind of doing that at your own peril if you're not at the very least aware of what's happening in the industry and how things are changing.
Yeah, I'm really appreciating these insights here, and I've got another question to add. And on that note, I'd like to say to our guests in the audience today, please feel free if you have questions for our panelists, submit those in the Q&A tab on your screen. And we'll be sure to have a stack of those waiting for to wrap up the end of our conversation in a few. So adding another question, another layer, how important is coordinated control logic in improving efficiency and performance? And what does, forgive me for the air quotes, what does good look like in practice?
Yeah. So control of the vehicle application and the vehicle level is really what the end user thinks about. At the end of the day, if it doesn't feel as good as the ICE counterpart, customers aren't going to pay for it. So you have to be at least as good, if not better. What we're also seeing is from markets, the customers aren't really willing to pay more for electrification. They're willing to pay the same for the same experience. And where we see that customers are interested in a more premium experience, a lot of that time, that premium experience is expressed through operator comfort, specifically reduced noise. We've heard numbers that are very optimistic on where the market is trying to go to, all the way down to below 55 dBA. To meet that, that is an enormous challenge for us to overcome. But it is a challenge that we can overcome, but it's really hard for us to do. And if it was easy, anyone would, right? So it's important that we're thinking about these types of things as we're thinking about the application, making sure that we're considering those when we're designing on the front end, and being careful with our trade-offs as we're going through development.
I think that's very well put. I think that the important part of that question too, I would like to point out, is a coordinated effort. So as with any kind of new design we're doing, electrification, hydraulic optimization, hybrid, it's important for us to sit with the customer and define that business need and impact that they're looking for. And then from that, we can come up with that coordinated control logic design to fit exactly what they need. As just like Joseph said, if it's lowering that noise contamination that you have within your application, or some other business need you're trying to meet, that's what defines what the solution is going to be. And if we can tailor that solution to what that business need and that business impact is going to be, then we're looking at a win-win situation for everybody.
Okay, kind of in keeping with those real world kind of applications examples, let's talk about, or let's have you guys tell us what some of the biggest challenges you see might be during commissioning and integration in those real world applications.
Yeah, there's quite a few challenges when we're talking about any kind of commissioning project. If everything is going to go, perfect, you don't have an issue, then you really haven't commissioned anything. So we all know we always run into some kind of issues. When it comes to the electrification side of things, as I mentioned before, when we have all these different components come together talking, they could all be talking the same protocol, such as CAN bus, but different vendors implement different messaging. So to get all those communication protocols to that one communication protocol, to be able to talk without any kind of handshake issues or ghost faults, it's important to have that system integrated to work through those kind of communication issues. Thermal environmental impacts. We always have that theoretical design that's going to work perfectly on our computers. But once we get into the real world and we realize it's minus 20 degrees outside, or it's 120 degrees outside, it might have a different impact on the system that doesn't show up in theory based. The physical disconnect. We look at an electric system versus a diesel driven system. Electric motors give you instantaneous torque. So you can have more of a physical vibration, mechanical stress on a system that you would not have on a diesel application. So fine tuning during commissioning is a very important part of it, to fine tune that electrical system because it's so much more powerful and so much more power on demand. Then wiring issues always seem to be a big issue. Most OEMs opt to wire the prototypes on their own versus using a wiring harness, which we see leads a lot of time in commissioning to do some rewiring, verifying terminations, ohming things out, the routing, the sizing. So that becomes a big upfront issue when we come out to commission things. That's why we do push an option to do wire harnessing, because it does save a lot of time on commissioning. And I believe Joseph has a pretty good example of some wiring issues that he's run across in the past.
Yeah, absolutely. So the one thing that always sticks out to me when people commission is EMI. This is something that comes up on every project just about, to a greater or lesser extent. I shared with these guys the other day when we were talking about this. We had a customer that had already had a vehicle that had started up. They were already doing low voltage electrification for their machine, and they were switching from low voltage, meaning like 350 volt. They were switching from 350 volt to about 550 volt to get better power density, basically. And when we got a phone call from them, they were pretty mad at us. They said, "Your inverter is junk." I said, "Well, what makes you think our inverters are junk since you've used us for years?" And they said, "Well, we thought the batteries didn't work because we couldn't get startup to work. So we had the battery guys took they took the batteries back to their facility. They tested them on a bench. They said nothing wrong with these batteries. It has to be your inverter. That's the problem." So they're pretty mad with us. We said, "Can we come out and look at your system?" So we did. And when we got out there, we saw some pretty significant problems with their wire glands. Specifically, sorry, their cable glands. Specifically when they were trying to wire things through a bulkhead connector, they left about a half inch, or I don't know, like 1.25 centimeters. Somebody help me out with the conversion here. Of shielding exposed, which was an enormous amount of EMI. We pointed this out to them, and they said, "No, no, 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 no. This can't be a problem. This is the exact same procedure that we use on all of our low voltage applications. Nothing here has changed. It has to be your inverter." I said, "Okay, we make mistakes every day. Can we test it?" And basically, what we did is we wrapped it in some aluminum tape or aluminum foil just around where those connection points were, and we reduced EMI by 85%. Now, I tell this story not to disparage the OEM, but simply because electrification is a different challenge than many of our customers see every day. Even when we have customers that do already have electrified vehicles, challenges can show up that they haven't already seen based on the way their existing system can look. And like, having that expertise when you go in to help them and to be able to give them a well-commissioned system at the end of it is critical. It's not about components, it's about systems, and it's about expertise there.
And I love these real world examples, and I'm kind of tease us up for our next question. What lessons from the field, both of you guys, have influenced how you approach system design today? That was one good example.
Is it me?
Yes.
System design. Real world experiences that we see in the field that influence that. We've already touched on NVH, so I don't think I need to hit on that one. But also, efficiency is still absolutely essential in this space. Specifically, if you're not thinking about how your pump operates with your valve, operates with your actuator, and how your pump and motor are talking to each other, where they're operating at an efficient set point, you're not really thinking about your system, and you're going to run into big problems. We had another startup where uh, somebody else was doing the vehicle level integration, and all of the parameters for our inverter and motor were modified to what they felt was an optimized set. And they had modified them to a parameter set that was unusable. We changed them back to default, and the solution was basically, I mean, the solution basically worked at that point. So making sure again that, your components are talking to each other and you have that team of experts in place that understand not just your product, but the entire application is critical.
Very well put. And again, it kind of goes back to as Joseph and I were talking about earlier. Having field engineering experience in the past helps you design that upfront system based upon something we've learned in the field quite extensively is keep it simple. So the simpler you keep the system, the better it is for everybody. The benefit of these electrification hybrid systems is that you can actually minimize the hardware design to be very, very simplistic. And then the dynamic design, again, is done in the software side of things. These inverters are no longer just inverters. They're inverters, controllers, VFDs, PLCs, soft starts. They can do so many things with an off-the-shelf software package that we've really not had access to before. that you can really do a lot of the system design within the software. And then the user interface is just that same Windows type user interface that the operator is used to using. And it's a very simplistic hardware design. So keeping it simple helps a lot with actual field applications. Some of the other stuff we run into is the battery sizing range anxiety issue. So on prototypes, normally the battery sizing is oversized because of range anxiety. Some of the real world data lessons we've seen is that we can downsize those batteries by almost half sometimes based upon data logging that we put on these prototype machines and show the customer that you really do not need a 10 kW battery. You can operate fine with a 5 kW battery, which is really a large cost associated with an electrification system. So that's just a couple of the real world examples we've seen.
Right. Okay. And I believe also one of the points that you made earlier this week, Shane, is early testing and iteration are key, right?
Oh, absolutely. There's not one solution to any given application. So there's probably 6 different solutions. So as we go through the initial theoretical design with the customer, it's a collaborative effort, as I mentioned before. We work very closely with the customer from the business impact side to the duty cycle energy usage side, which is huge. How much torque do you need? How long do you want this to last? What motor size do we actually need? It's not going to be as big as the engine you had because we're not designing for max horsepower. We're designing for efficient horsepower and intermittent horsepower usage. So all that comes into play when we're doing that design. And the first iteration is not normally or won't be the perfect one. That's where testing comes into play. We'll test it. We'll go with a different iteration after we get some results from that testing. Data logging is very important. Remote diagnostics, we use that for predictive analysis and for troubleshooting. All that ties into the different iterations that you work with through prototyping to mitigate that production cost of the perfect design when we finally get through those iterations.
Shane, you're
Well,
speaking my language here. In another life, I was a vehicle test engineer. So really, I mean, this is bread and butter, and it's fundamental to how we work at Danfoss as well, right? I mean, anybody can try to sell a PowerPoint, but when you actually are showing how a vehicle operates, showing them that you believe in this so much that, in the past you might have invested in your own vehicle and done the conversion on this, understanding that deep level of knowledge that's needed when you're actually going in and doing these conversions to show you can be a real partner, that's essential to build your credibility and to maintain like your position within the market, because bluntly, that's the expectation. So you have to be able to meet it.
Well put.
Love it, guys. Leaning a little bit into the efficiency that Shane just touched on, let's talk about performance efficiency. This question might be a little broad given some of the complexities of these machines, but what engineering decisions have the greatest impact on those points of efficiency and overall machine performance?
I think Joseph hit one of the top ones right off the bat earlier with lead times. So when you're looking at doing these kind of electrification hybrid machines, lead time needs to be considered as part of that engineering solution. If you're sitting there saying, hey, I want to get something done in 4 weeks, and I really have no way to work with this lead time, it has to be done in 4 weeks, you may end up with a box of equipment that you never use, that you're sitting out holding out paper. Lead time is important because most good solutions are going to take time to put together, time to engineer properly for them to work properly. So that, I believe, is a very important part of the overall cycle. The full system design approach, again, a lot of the things we see is just replacing the components. Hey, I want to remove this 100 horsepower engine and put a 100 horsepower motor in. Well, what about optimizing the hydraulics to where you don't need 100 horsepower? Now you only need 70 horsepower. What about doing more of a modular design where we put, a bigger pump here on the main function, and then we put smaller modular pumps and motors on some of the auxiliary functions? Managing weight and space, that really comes into play when you talk about electrified machines because batteries are heavy and they take up a lot of space. The good news is the motors are smaller, so you make some gain there. Remote access capabilities. I really can't speak enough about this, especially when when you're doing a system integration approach, you're doing the prototype, and especially when you get to production units, being able to troubleshoot something from the East Coast to the West Coast remotely saves tons of money and time as opposed to sending out a technician. With the software capabilities we have now, with the inverters we use and the fault codes that we get and that we can see, most of the troubleshooting can be done remotely. So that's a very important part of the overall process. And then I'll go back again to just keeping it simple. If we can keep the design relatively simple, we work with the OEM to train them on how it operates, why everything's designed the way it's designed, so they feel comfortable with it. We mitigate all kind of failures in the future by doing that.
One other thing I'd add as well is understanding the duty cycle. Shane touched on this a little bit earlier, but it's sometimes surprising how our OEM partners think about the duty cycle of their vehicles today and how their vehicles are actually used every day. So, as Shane mentioned earlier, an engine is generally sized for peak power usage. Whereas if you're going to a full battery electric solution, your inverter is designed almost always for continuous use. So if you right away take a look at your inverter and say, I need peak power, and that has to be the number that my inverter is designed to, you've already sized your system inappropriately. Understanding how long you need to run at that peak power is something that that historically in ICE applications is not entirely understood. And understanding if you're running at that peak power for a longer period of time, what the thermal implications of running at those at those settings are. So really having that deep level application knowledge is essential here again. Um, Understanding how that fits into the cooling package and what pros and cons you can trade off to, okay, we'll have to increase our cooling package slightly to be able to downsize our inverter. And that has a net gain on our bill of materials of minus, $400. Yeah, that's something you should consider for sure.
Well, I think a lot of these points too are tied off to the word we didn't say, trade-offs. So how do you balance the trade-offs between some of that performance and efficiency with system complexity?
I think that's what engineering is, right? Unfortunately, the world is not as simple as this is the perfect one size fits all solution for something. And that's why we see so many different electric architectures out there, right? There are some places where a serial hybrid makes perfect sense, others where a parallel does. There's some places that, again, today it doesn't make sense for us to electrify. Some places that it would be crazy if we weren't electrified, full BEV. Making sure that you understand your customer's use case, making sure you understand what your customer needs when it comes to those trade-offs. That's the difference between project success and failure, and that's the definition of design and engineering. So I think that is the job here.
I would add one note to that is, and when you're looking at the trade-offs, you really need to look at the total cost of ownership.
Yes.
Some electrification solutions are going to cost more upfront, but your ROI on that could be 1, 2, or 3 years. When you look at that total cost of ownership, many times we deal with OEMs who have a capital budget group that's completely isolated from the maintenance budget group. So those two worlds never come together. So that total cost of ownership never really comes into the conversation. It's important to note that while some systems may cost a little bit more upfront, that total cost of ownership will see a very, very quick ROI, like going to an electrification or a hybrid solution. But that's something that needs to be considered when you're looking at all your trade-offs of this particular system design.
Thank you for that perfect transition, Shane. My next question is covering a little bit of that hybrid technology. So how does that hybrid tech factor into the future of electrification, particularly when optimizing these hydraulics, controls, and overall system performance?
Yeah, so hybrid solutions have become a great alternative to any OEMs who don't feel like they're in a position to go full electrification. So some of the generator starter motor solution that we have is like a motor that attaches directly to the flywheel of an engine. So this offers up to a 65 horsepower boost to the engine for intermittent horsepower and a 45 horsepower boost to the engine for constant horsepower. So what this allows an OEM to do is to downsize their engine so they can reduce not only the engine costs, but fuel costs as well. Sometimes they can get below that 75 horsepower threshold that we all know require. Once you pass 75 horsepower, you have to put those expensive after fuel treatment systems on there for DEF and SCR. So you can reduce a lot of costs when you're looking at a hybrid solution by really downsizing your engine, your diesel, to under 75 horsepower. Also with this solution, when you're not offering the horsepower boost, this solution acts as a generator. So it'll generate recharging power for your battery system when it's not in motor mode. It can also act as a starter for your engine. And if you install a clutch in between the diesel engine and this motor, you can also decouple it and operate in all electric mode. So if I have a function where an application where I have to operate inside sometimes, I can decouple the diesel engine, operate in all electric mode. Then we can move that asset outside, kick on the diesel engine, and recharge the system. So the good news about this solution is all these things have seamless communications. So the motor is talking to the battery, the inverter is talking to the engine. It monitors the engine for when it needs that horsepower boost. It'll automatically kick into motor mode and give that horsepower boost. When it's not needed, it'll automatically kick into generator mode, generate power for that battery. If you don't need it or motor mode or generator mode, it'll just sit there and stand by and say, let me know when I'm needed. And all this happens in microseconds. So it's seamless. And then the software solution that these inverters come with, as I mentioned before, it's so dynamic. This is kind of a set point software that you plug in. Say, hey, this is my load, my RPM set point where I want you to kick into these modes. And the software automatically handles all this. So it's really, the hybrid solution has become a very, very good alternative to full electrification with a lot of benefits at a low entry cost point and while saving the OEM money on those larger diesel engine applications.
I guess just to add to that, putting a little bit of a historical context on this as well. When we were kind of in the generation one electrification craze, there were a lot of people who said we just need to electrify for the sake of electrifying. And we definitely saw situations and applications where it didn't make sense in the way that the architecture was designed, or it was less efficient or more costly. And these considerations weren't taken to the extent that they should have been. And bluntly, that's had an impact on some people's willingness to convert long term. I will say, though, if you take a slightly wider lens to where we are today, we are seeing that end users are still very interested in electrification. This didn't put them off at all. In China, if you look at the EV market writ large, there's almost product parity between electric and ICE applications. That's a statement that, the market wants this. This is something that's real. And so making sure that we're still addressing that demand, but we're doing it intelligently in a way that makes sense for our end users and our OEM customers is how we will succeed in the future.
Well put.
Well, bringing me to kind of our future outlook here, keeping an eye in that direction as electrification continues to evolve, what changes are needed in how OEMs approach system design and integration?
So the first thing, since we are talking to a lot of Europeans on this call, I want to make sure that I'm acknowledging it. Functional Safety and Cybersecurity Resiliency Act are essential right now in order to continue in that market at all. Functional safety is not optional in most cases, and not just in Europe. In most cases, to reduce liability and to make sure that you are following process and you're actually building a good, robust system, it is just required. The addition of cybersecurity here is a good one. It gives you a strong whole vehicle system health and wellness overview, which is something that's absolutely needed in today's world, especially when we're talking about things like linked applications, as Shane was mentioning before, that you could be doing uploads, downloads. Not having this it's not only not an option from a sales point of view, bluntly, it's the only responsible path forward. So having that in place is an excellent, I think, starting point for this conversation.
Yeah, I agree with that completely. And as Joseph mentioned, Europe has really adopted electrification a lot quicker than we have in North America. From the North American standpoint, we have to adopt that cultural change within our own environment. We need to consider the life cycle focus versus the initial upfront cost. It is a changing technology. I mean, battery technology is changing monthly. We're seeing new technologies come out. We're seeing battery costs start to come down, which starts to make electrification more of an inviting option for a lot of our OEMs as we see some of those costs come down. We've already seen it in permanent magnet motors and inverters. We see those costs starting to drop some. So as we see the technological revolution in electrification products start to take over and start to come down a little bit in cost, I think we'll see more adoption, especially in North America, on the electrification systems. So that is part of that cultural change that I think we'll see. And then education. As always, it has to be an important part that we're not just supplying solutions to our customers, we're educating them along the way and showing them why these solutions make sense, why we're going down this road, what business impacts, how this affects their bottom line. Again, if the customer is not making money, then it's not going to be a really good solution. So as this regulatory environment we live in is changing almost daily, we need to focus on the important things like the cultural changes, the education to our customers, and the future technology that we're going to see coming down the road.
And another great place for that education might be a resource called oemoffhighway.com if you want to check that out. Let's take a couple questions here. First up, and this is kind of a basic, but we've got to address it. A lot of people are still in this place. For OEMs just starting their electrification journey, what is the first step they should take to move toward a more integrated kind of system level approach?
You want to take this one, Joseph?
I'm happy to. And I think we've touched on it a bit today. Understanding your application, understanding what is important to your customer, understanding what your duty cycle looks like. Those are an excellent place to start. If you have those and you understand what value you're trying to bring by electrifying, you're 85% of the way through the problems. I mean, all the technical challenges still remain in front of you, but where a lot of the difficulty on these projects come up is when those three pieces aren't clear to you, and suddenly things that could be very simple to solve become very complicated because you can't kind of zoom out and understand it from a high level.
Just to add to that a little bit, so as I said, we have a power sync process we go through that addresses that. So we actually have stage 1 through 4, where stage 1, we're looking at your business needs, your impacts. What are you trying to accomplish? As I mentioned before, stage 2 is going to be that energy focus. Okay, how are we going to size out this system to match your business needs? Stage 3 is when we start putting together, your ballpark pricing, your BOMs, your wiring diagrams, and then of course stage 4 is your prototyping and your commissioning. But as we mentioned before, that's where your system integrator comes into play. They'll work with you from stage 1 all the way through completion and the life cycle of the asset to make sure that you're not set up to fail. You're going to succeed, and we're going to help you walk through that entire process.
Nice. Thanks, guys. Okay, so we're gonna got a lot of questions rolling in. I'm gonna keep hitting these back to back here. What improvements in the overall efficiency of the electrified hydraulic systems are you seeing? Are the efficiencies lower, higher, or exactly what you were expecting? And I think I'll hand this off to Joseph to answer first.
Sure. I'm glad that you specified within the hydraulic system. If you're talking about overall vehicle, we just get a lot of energy back right away by not having conversion losses from going from an internal combustion engine to mechanical power to hydraulic power back to potentially mechanical power again there as well. Staying on or reducing that complexity, reducing that chain makes things easier, and you get some efficiency there. But since you did specify specifically on the hydraulic side, It depends, is the short answer. On the maybe simplest or least complex hydraulic systems that we're talking about, we are still seeing improvement, just simply because we're much more precisely and much more precisely and comfortably controlling how our pumps are moving compared to an internal combustion engine. And so just through that alone, we're seeing 5 to 8% efficiency increases. When we talk about things that are really advanced system architectures, those numbers get to really, really interesting numbers, like over 50%, over 70% efficiency improvements in systems. Now, as I said before, the question here is, does the cost justify that added expense? And that's an application by application determination.
That's well put. And again, as we mentioned before, on these applications, the diesel engines are sized to the max horsepower. From the electrification solution, it is more sized to the constant horsepower, with the permanent magnet motors able to hit that max horsepower intermittently, depending on the duty cycle. So you save a lot of efficiency on that way by hitting only the part of the horsepower you actually need, instead of constantly providing you that max horsepower.
Unmute. Moving into our next question. How about, what's one trend or technology in electrification that you think will have the biggest impact on machine design over the next 3 to 5 years? It's a big one.
I personally see one of the impacts is battery technology. I mean, as we start talking about solid state battery technology coming down the pipeline, then range anxiety goes away. So we don't have to worry about the fact that some applications need a battery bigger than the application to operate for the 8 hours they want to operate, or they'll need some kind of hybrid system that recharges as we go. As battery technology evolves, that range anxiety is going to go away, and it's going to open the door for a lot more applications that weren't being considered for electrification solutions.
From my side, I'll maybe just hit one or two really quickly. Inverter technology, battery technology, those are absolutely essential. We're seeing voltage changes within the market on an increase in voltage of what's being accepted in different parts of the world. Going from a 2448 volt system that we would have seen a handful of years ago, and now people are talking about 96 volt instead, even higher. And the same is true in the high voltage side of things as well, right? A handful of years ago, we were talking about 350, 400 volt as kind of the primary factor. If we're looking at even the on-highway space, a lot of those are going to 750, 800 volt at this point, even higher in some cases. So that shift is certainly something that's going to affect systems and system costs as well. Integrated components is something that's definitely more and more of a discussion. We talked a little bit before about EMI. So if you can reduce the total number of high voltage wires that you have to run across your system, this is something that we're starting to see is, again, it's not every application, but in many applications where OEMs are happy to reduce the number of components needed in a system. And then finally, one that people might not be thinking about every day here is autonomy enabling. Electrification, when we talk to OEM customers, is a key enabler towards an autonomous future. They want that precise level of control, the machine level feedback, the understanding of where their vehicle is in space that you're going to get from an electric machine that you might not get nearly as precisely with an internal combustion engine. And so when OEMs are thinking about autonomy and self-propelled vehicles, self-operating vehicles moving forward, most of the time they're thinking about electric machines long term.
Great. Okay. Stay with me, guys. This one might be a little specific. Our next question asks, if converting an internal combustion engine off-highway machines to either hybrid or fully electric, is there much cost benefit to be had from optimizing the hydraulics to an electric prime mover at the same time? Or is it generally more cost effective to try and match the electric motor output to the internal combustion engine and keep the hydraulics the same?
Well, I personally think you look at the overall system design because if there's not a way to optimize the hydraulics, then as a system integrator, we'll tell you, hey, the hydraulics look fantastic. But if we can optimize it by either adding some manifold designs in there to shorten some hose runs or to lessen some service issues you may have on your existing system, or go from a vane pump to a piston pump, or some kind of optimization, we'll at least present it as an option, saying, because we look at, again, the system, the total system. So we'll present it as an option saying you can keep your hydraulics with just replacing an internal combustion engine. And here's your solution. Alternately, here's a solution where you have optimized hydraulics. And then we can actually downsize your internal combustion engine or the motor equivalent based upon the efficiencies we've gained from this optimization.
Yeah, I think you're right. Again, it goes back to what is the key driving factor for electrification here, or what is the key reason that our customer is coming to us about electrification on this. If cost is a major factor here, you know, there are very good solutions that can work with relatively low voltage and relatively inexpensive hydraulic solutions. If you're much more concerned about efficiency of your system, if you're much more concerned about, noise or operator comfort, if you're much more concerned about very precise operator control, there are ways to optimize for all of these things. So which one is it more cost effective to do A or B? Is it more energy efficient to do A or B? I think those are all application considerations that you need to weigh as you're going through it. And another reason why you need to have experts in all of these different areas.
Tying into a little bit of that application specific kind of conversation we're just having, the next question asks or starts with hybrid light towers are a great application that have a great ROI. What other electrification applications have you seen that make sense economically so that machines are easy to sell?
It's a loaded question. So I know we've seen applications across the board. If we look at percentages, 15% across the construction market, 15% across ag, 15% across the military. It really spans all the different markets. It really is application specific. Turf applications, you think, well, that's one obvious one. I don't have to worry about hydraulic contamination on a green or a golf course or on an expensive turf application. The ag applications, again, Joseph mentioned earlier, autonomy. As we talk about labor shortages, it makes sense on ag applications to electrify those machines and to look at autonomy as a solution. Same thing with the construction industry, especially when you talk about noise contamination. Be able to work at night around residential areas. Well, that's a great electrification solution because you can operate below that dB requirement of that recreational environment. So it really does span across a lot of different markets in my eyes, and it really is application specific.
I also want to make sure that people don't fall into the trap of thinking electrification means small. Some of the most challenging and interesting applications that I've worked on are very, very large applications. Huge, mining loaders, those types of things. There is some regulatory pressure in the mining space in particular where it makes a lot of sense if you don't have to run or dig an entire separate mine shaft just for exhaust, for you to go emissions free underground. If you have a power plant on site because you have the resources that are being collected as a byproduct of what you're mining, grid connectivity might make a lot of sense for you. EV doesn't necessarily mean small. EV means you have to think about what your application is and how it's being used. And I think that's true for every application. So I guess what I'm saying is EV is on the table for every application. It's just a matter of if it's the right time and the right architecture.
Okay, it looks like I've got one question to maybe close us out here today. Looking back, and this might pull on some personal experience for you guys, looking back at recent projects, What's one electrification misstep or mistake that you see most often, and how can others avoid it?
Missteps that I see regularly.
May depend on the
You know,
application,
yeah,
so
and
just like we're talking about.
I'm kind of trying to decide which way I want to take this one. Missteps can happen in every single phase of electrification, just like they can in any sort of design in sort of any sort of design application. So again, in understanding why you're doing what you're doing, you can misstep there and say we're chasing A, and really B is where you're targeting. Um, when you're actually going through component selection and design, um, I've seen everything from people selecting the wrong size pump, the wrong type of pump, the wrong type of valve, where it's an on-off valve instead of a proportional valve. I've seen where people select open center pumps and they meant to select closed center. I've seen people select controls that are normally on versus normally off incorrectly. I mean, you could go wrong a million different ways, and people do. I've seen applications where fluid conveyance was routed so poorly that they lost like something like 14% efficiency on their total vehicle application, and that's something that a lot of the times isn't considered until the very end of the hydraulic circuit. Um, I've seen people start up their machines without pre-charging circuits or by overcharging pre-charged circuits and having some exciting events occur electrically around them. There are a million ways you can screw up, and like I said, it happens, right? It's it's minimizing the number of ways that those failures can happen is why you need somebody like us.
Yeah, I agree with you completely. You just led right into my piecemeal and components. So while we offer a total solution from a system standpoint and in our concept designs, we'll have customers who say, well, I Googled this and I can buy this on my own. And then now you're trying to piecemeal things together. And then you run into an application where somebody just put 450 volts on a 48-volt bus. Well, I mean, when you piecemeal things together, there's going to be a lack of communications, a lack of collaboration, and things are going to get lost. And you're going to run into those inevitable problems upon commissioning where they just don't communicate or come together like they should. So again, the system integrator approach really solves a lot of those issues and helps you actually troubleshoot through them when they do happen. Because as Joseph mentioned, as we've all been involved in any kind of commissioning, rarely is it going to go 100% without any kind of issue at all. You're always going to run into something. But having that team on the ground to be able to work through those issues is unbelievably important to get that application off.
Okay,
I mean,
everybody. Oh,
bluntly,
go
it
ahead,
can be the
Joseph.
difference. It can be the difference between a commissioning that, oh, we caught this mistake, to, oh, we need to shut the facility.
Absolutely.
And with that, that's our time for today, which will bring our session to a close. Thank you so much to our amazing panelists, Shane Fauché and Joseph Glidden, for joining us today and sharing their expertise. Stay tuned for more from the Future of Electrification Conference, and be sure to check out more sessions at futureofelectrification.org. Thanks again for being here with us. Have a great day, everybody.